In part 2 of the Unit 6 notes, we will be covering properties of ionic compounds. Ionic bonds are extremely strong, which means they require a large amount of energy to break. This causes ionic compounds to be room temperature solids. Extreme temperatures must be reached in order for an ionic compound to melt. In the table below, we have 3 ionic compounds versus 3 covalent compounds. You can see that all 3 of our ionic compounds melt at fairly high temperatures, all well above 500 degrees Celsius, and that our covalent compounds melt significantly lower than that. Ionic compounds are hard, rigid, and brittle due to the strong attractive forces that hold the ions in place. When an external force is applied, if it is strong enough to overcome the attractive forces, the crystal will crack and break apart. This occurs because the applied force causes the ions to reposition, resulting in like charges being near each other. You can see an example of that in our diagram here. So we have sodium and chlorine, and similar to what we talked about in the last video, each one of our positive ions is completely surrounded by negatives, and each one of our negatives is completely surrounded by positives. This leads to a very stable structure overall. But if it's hit with enough force, which is shown here with the hammer, those ions could potentially reposition, which results in negatives next to negatives and positives near positives. Like charges will repel, which causes this structure to shatter. Most ionic compounds dissolve and dissociate in water. Dissociation is the separation of ions which occurs when an ionic compound dissolves. The polarity of water, which means the molecule contains partial positive and partial negative charges, helps the ionic compounds to separate into free positive and negative ions. We can see an example of this in the diagram on the right. This is our water molecule. This end is partially negative, and this end is partially positive. This occurs because the electrons are pulled more closely to the oxygen since it is more electronegative. When this comes into contact with the salt structure, the oxygen, which is partially negative, will attract the positive portion, which is the sodium. So you can see water molecules surrounding a positive sodium ion here. And the positive end, the hydrogens, will completely surround the negative portion, which is the chlorine ion. The water in this instance is acting kind of like a key that helps to unlock this otherwise very strong and stable structure. If you were to draw out or write out this process of dissociation within a formula, you would start with your original compound with an S showing that it's solid, and when it goes into the aqueous phase, you would separate each of the ions into positive and negative charges with an AQ showing that it is aqueous. Ionic compounds cannot conduct electricity in a solid state. Since the ions are locked into place within their crystal structure, they are not free to move. If they were to melt, or if they were dissolved and dissociated into a liquid like water, they can conduct electricity extremely efficiently. This is due to the fact that ions are free to move in a liquid or aqueous state. In our diagram below, we have an example of distilled water in a beaker. In this instance, our light bulb is not lighting up because the distilled water is unable to conduct a current. Here we have a solid ionic compound. We put each of our leads into the ionic compound here, but again, within this structure, the ions are not free to move. When we combine these two into the same beaker, the ionic compound is going to dissociate into the positive and negative ions. And now that the ions are free to move, they are able to conduct a current, so the light bulb is able to go off. Many ionic crystals, including gemstones, have brilliant colors. These colors are due to the presence of transition metals in the crystal lattice structure. Remember, the transition metals are the ones within the D block of the periodic table, the middle section. Transition metals have electrons in the d orbitals, and if they are partially filled, there will be unpaired electrons capable of absorbing visible light in order to promote electrons to a higher energy level. The wavelength of light that they absorbed is removed from the light, and this is going to impact the type of colors that can be emitted from the structure. In our first checkpoint, we are asked a true-false question. A compound with a melting point of 500 degrees Celsius, which is hard, brittle, and conducts electricity when dissolved in water, is most likely an ionic compound. We saw within our properties earlier that compounds which have very high melting points, in our examples much higher than 500 degrees Celsius, were likely to be ionic. And that is definitely the case here with 900 degrees Celsius. We also saw that ionic compounds could be hard, brittle, and they would conduct electricity when either dissolved in water or within their liquid state. They would not conduct electricity within a solid state. Based on all of these facts, we can conclude that this statement is going to be true. For number 2, we are going to explain why ionic compounds will shatter when sufficient force is applied, and we need to reference the atomic structure within the compound. Well, we know that the ions within this crystalline structure are going to be organized in such a way that the positives are next to the negatives and the negatives are next to the positives. If we apply enough force to that structure, we can have those ions realign so that positives are next to positives, negatives are next to negatives, and those like charges are going to repel one another. So the ions in the crystalline structure will change positions This results in positive next to positive, and negative next to negative. This concludes part 2 of the Unit 6 notes. When we come back for part 3, we will be naming for binary ionic compounds.